right. Thanks, Justin and CLF team for having me here. My name is Will, and like Justin introduced me, I lead materials performance engineering at Brimstone. My background is in structural and materials engineering, and I'll talk a little bit about Brimstone and our approach to carbon negative Portland cement, and also SCM for structural concrete. So as probably all of you know here, carbon emissions related to the production of cement and concrete has been a known issue for several decades. These stats are probably numbers that you've seen in different presentations and literature, but 1 ton of cement is about 0.8 tons of CO2, roughly. And it's a market that continues to rise in demand. There will always be a need for cement production and for concrete. And the general process of how to make Portland cement hasn't fundamentally changed in about 100 years. And for us, it's an opportunity to enter the market with a new product, with a product that addresses the CO2 while also making a cement that people want to use. So before I kind of get into why Brimstone cement is different and carbon negative, I think it's useful to understand how conventional Portland cement is produced today. So the raw feedstock for Portland cement mostly consists of limestone and clay. Limestone provides the calcium you need for cement, and the clay also provides silica, and both of them will also provide alumina and iron. As part of cement production, roughly 60% of the CO2 related to cement production is actually related to the calcining of limestone. So limestone is calcium carbonate, calcium CO3, and as part of the cement production process, CO2 is emitted in order to obtain the calcium needed for later processing. So 60% of that is just related to the limestone itself. The balance of the CO2 emissions is related to energy. And a lot of this is also related to, we have to heat the material up to 1500 degrees Celsius in order to clinker it and produce useful products that can actually hydrate with water at room temperature and make concrete. So out of typical cement production in the United States, we will make SCMC 150 Portland cement, either type 1, type 2, or type 2, type 5 in most markets. And then what you could do at the ready mix level is include supplementary cementitious materials. These are materials that can be industrial byproducts like fly ash or slag, or calcined rocks like calcined clay or metakaolin. These have their own ASTM designations for specifications. And you can mix cement and SCMs in addition to water and aggregates, and then you'll get concrete out of that. And I'm pretty sure everyone kind of understands this process fairly well. There are some challenges with how to approach concrete decarbonization once we kind of think about the things that we can change. First, we have to understand that, again, 60% of the CO2 is actually tied to the calcining of the limestone. And so that is just from the feedstock itself. Largely at the ready mix level, reduction of CO2 has often, a strategy for it has often targeted the replacement of cement with different SCMs. Very popular SCMs are fly ash and slag. The problem with some of these SCMs, particularly with fly ash, is that they are industrial byproducts. And because fly ash comes from coal combustion power plants, because those power plants are gradually retiring and being decommissioned, the availability of some of these SCMs like fly ash is going to dwindle in the future. And so a strategy of replacing cement with SCMs will be more challenging as some of these SCM demands, or as some of these SCM supplies go down. There have been industry-wide strategies like type 1L Portland limestone cement, PLC, which aim to also reduce carbon emissions through different strategies. For type 1L is by reducing the clinker in your final cementitious product. But these strategies only provide small reductions to overall CO2. So kind of understanding these things, or actually before I get into Brimstone, let me talk about the SCM a little bit. So even though, the main focus is on cement, because one of the primary strategies of reducing CO2 in concrete is by replacing cement with SCM, the two will be always tied together in terms of like an overall decarbonization strategy with concrete. And I talk about fly ash in particular just because fly ash is currently used at high substitution levels. You can use it at substitutions in excess of 30% in structural concrete. And as you can see from this graph here in the dark blue, that just shows how much fly ash is being produced over the past 20 years or so. But in light blue, you can see how much is being actually used. And so what this shows me is that the supply for fly ash is going down, but the demand is actually staying about the same. And so this will be problematic in certain markets in which SCM is a very has very regional availability. And so certain markets might not actually have access to a lot of SCMs in the future, or the SCMs that they prefer to have in their concrete mix designs. So, I think there are different companies and startups that are approaching the cement and concrete decarbonization. And I'm just going to tell you what Brimstone's approach is. Again, there are different approaches, but this is one that we know can work in the future. So for the fastest implementation of a cement in structural concrete, and I say structural because I mean a cement that can be used at all different compression strength levels that you would expect for compression for concrete, from like sidewalks all the way to seismic resisting members. The cement that we produce has to be the same material. It has to be ordinary Portland cement. And so this is important to us because then we produce a material that has the same cement chemistry as you would expect for a conventional cement. It has the same physical properties like fineness, which can affect workability, pumpability, and other properties in the field. And by producing an ordinary Portland cement, it helps us provide a material which has predictable setting properties such as setting time, which is important for contractors, strength development, which is important for structural engineers and also contractors, and other major properties that you would associate with structural concrete. What's also important about having our material be an ordinary Portland cement is that it can meet the ASTM requirements for Portland cement, which is ASTM C150. This allows us to implement the material as quickly as possible through project specifications. Through your normal project specs for structural concrete in that section, we'll often have Portland cement conforming to ASTM C150, and there might be a specific type that project needs, typically 1, 2, or 2.5, depending on where you are. But we expect that if our cement was not an ASTM C150 cement, that there would be significant hurdles in actually getting material out and actually meeting typical project specifications. From an economic point of view, our material has to be cost competitive or cheaper. I think that probably makes sense to all of you here. Our intent is that once we're at full scale, we're not really going to charge a premium for our material, even though it is carbon negative. And the third point, just due to more recognition of the carbon issue with Portland cement, our material has to be carbon neutral or carbon negative for it to be competitive in the future. And we think that these three things put together produces a material or guides a material that contractors and engineers and all stakeholders in the construction industry actually want to use, and covers kind of different reasons why you would want to use it. So with that, I'll talk a little bit about what makes Brimstone cement just a little bit different than conventional cement. So before I had tried to emphasize the role of limestone and how it actually is a significant part of CO2 emissions of conventional cement processing today. Again, 60% of carbon emissions are tied to actually calcining of the limestone. And so because of this, we actually started out with a different kind of raw feedstock for our rock. So we use something called a calcium silicate rock. An example of a calcium silicate rock is basalt. There's several kinds of rocks that can be generally classified as calcium silicate rocks. These rocks are very abundant in the Earth's crust. And so that is good for us because it lets us put cement plants down in a variety of different regions, which can be located near major like industrial area or major urban areas that need cement. And one of the most important things about these rocks is that there's no carbonates in them. So there's going to be no extra release of CO2 by processing these rocks as part of our process. And so we do have a proprietary process that I can't go into too much detail right now, but at the end of that process, we do produce an ACM C150 Portland cement. It produces the same chemical compounds that you would find in the clinker component of your cement. I won't go too much into cement chemistry, but our cement does rely on the same cement chemistry as conventional cement. It still has gypsum to control something called C3A in the cement, and it's ground and milled the same way as conventional cement. And so its particle size distribution will be the same, will be similar or the same as you would find in normal cement, same physical properties. As part of our process, we actually will produce a silica residue. And so pozzolanic materials or SCMs have pozzolanic properties which lets them react with certain compounds in a concrete system and allows the concrete to gain strength. SCMs are really good because they can increase durability, they can increase strength over the long term. They can obviously reduce CO2 from the cement by substitution. And so as part of a process, we end up with a silica-based residue. It's pretty reactive, it exhibits pozzolanic properties, and right now we project it to adhere to the specifications for ACM 618 SCM for type N natural pozzolans. And so as part of our process, we also provide, we can also provide SCMs through Brimstone. I'll stop there. And then a third product that we make, or a third product that's produced as part of our process, is a magnesium-based residue. And so from the same process, we'll also make this residue. What's important about this magnesium-based residue is that it can react with CO2 in ambient conditions, atmospheric CO2 in ambient conditions, and produce a magnesium carbonate product. This magnesium-based residue is not put into the cement and it's not put into concrete. It's just its own residue that will be set aside. But because it is CO2 sequestering, what that does is that in combination with replacing limestone with calcium silicate rocks, it allows our process to be overall carbon negative with these two important characteristics, being the replacement of limestone and also the CO2 sequestering with the magnesium-based residue. Again, this magnesium-based residue doesn't go into the concrete itself, but with the cement and SCM, that can either be blended or shipped separately as two different materials to a ready-mix plant. Add that with water and your sand and coarse aggregates, and then you can make concrete, kind of as you would expect. And so I'll actually kind of start wrapping up here. So at Brimstone, we think that in order for the fastest implementation of this material to be used in actual industry again, it has to be the same material, ACM C150 per cement. It has to be cost competitive at scale, and it has to be carbon neutral or carbon negative. In our case, it's carbon negative, again, because we replace the limestone with calcium silicate rocks, which avoids CO2 release from the limestone. And then we produce a magnesium-based residue that can sequester CO2 and react with it and produce a product after that. Currently for Brimstone, we have a pilot plant location in Nevada. Right now, we're working towards building up that pilot plant, which will be operational. We expect sometime in 2024, a year from now. And then that pilot plant will start producing relatively small amounts of cement relative to a full-scale production plant. And a couple of years after that, we aim to have our first full-scale commercial plant. And that's the end of my presentation. Thanks.